полугруппам. И мы рады приветствовать нашего первого докладчика, Ксению Перевозчикову. И она нам сейчас расскажет про то, что расскажет. Пожалуйста, Ксения.
Я начну сразу на английском, наверное. Thank you so much. Let me introduce myself. My name is Perevozchikova Kseniia. I am postgraduate student of South Ural State University. I'm from Chelyabinsk, Russian Federation. So first I wish to thank the organizer of the conference, and the topic of my presentation the Degenerate Nonlinear Semigroups of general mathematical filtration Boussinesq model. My talk will be a three-part. The first part we use the phase space method to construct quasi-stationary trajectory that is the solution abstract operator differential equation defined on the phase manifold. The second part we show that the solution can be continued in the time on interval from 0 to plus infinity in the case of dissipative operator M. And last part, we construct a nonlinear resolving semigroup of sheaf operators of Sobolev type equations. They obtained abstract result illustrated by Cauchy-Dirichlet problem for the filtration Boussinesq equation. Let's start by setting the problem. And then from middle of 20th century, this theory of semigroup of operators is one of main research tools to study the Cauchy problem. 1. For abstract operator differential equation 2. One of methods to find analytical solution.
I'm sorry, Ksenia, we still see the first, the title page of your slides. So have you switched to the next page?
Sorry, repeat, please.
Мы видим ваш титульный лист. По крайней мере, я вижу титульный лист.
Так, секундочку.
Yes, now we see the next slide. Yeah, everything is fine.
Видно ли мой слайд?
Да, да, сейчас видно следующий.
Окей. I repeat.
Yes.
And consider Cauchy problem 1 for abstract operator differential equation 2. One of method to find analytical solution to problem 1, 2 is to construct a resolving semigroup of operators. In the case of linear equation 2, the theory of semigroups of operators was proposed and developed by Henry Hiller, Kosaki Yoshida, William Feller, and others, and was widely used to study various initial boundary value problem for a question of mathematical physics. In natural science and technology, an extensive class of processes and phenomena can be modeled by partial differential equation or system of partial differential equation. His equations are not resolved with respect to the highest time derivative and have form 3. And such equation in a form 3 are usually called Sobolev type equations. For the first time, this term was introduced by Scholter, and problem 1 and 3 is difficult to study. The main reason is that the problem is unsolvable in principle of initial value U0, even if U0 belongs to a dense linear of the initial Banach space. It is relevant to search and describe the structure of set of initial value. Condition 1, Cauchy problem, for which problem 1, 3 has a solution. One of successful methods to study linear problem 1 and 3 is a theory of degenerate resolving semigroup of operators. So, consider the phase space of the model under study. Let raised H be real separable Hilbert space identified within conjugate space, and H and B be dual pairs of reflexive Banach space such that embedding for a dense and continuous. Let operator L be a linear, continuous, self-adjoint, non-negatively, and defined Fredholm operator, and the operator M belong dense. And operator M belong space of differential function at k quile and more or quile 1. And in view of the self-adjoints and Fredholm property of the operator L, we identify H includes kernel operator L is identically quile, so kernel L. This implies this implies a joint H, a quile direct sum co-kernel operator L and image operator L. Denoted by this symbol, closure image L in topology B and joint B. Then and joint B acquire direct sum kernel L and closure image operator L. And denoted by QQ projector, projector enjoys B along co-kernel L on closure image L. Then if X is a solution of equation 3, the solution belongs to set reset M5. Also consider the set co-image L in the form presented on slide, and the space B can be represented as direct sum B0 and B1, where kernel L equal B0, co-image L and B equal B1. Denoted by P the projector on B1 along B0. Before proceeding to the consideration of quasi-stationary symmetric we introduce several important definitions. A vector function and a vector functions and the point u0 belong as raised M. This definition show of a simple Banach manifold under given conditions. In what follows, the set M is called Banach CK manifold, modeled by subspace B1. If raised M is a Banach CK manifold at each of the point, then the following theorem is true. Suppose that the set raised m is a simple Banach CK manifold at the point u0. Then exists the unique quasi-stationary symmetry of equation 3 that pass through to point 0 u0. In view of classical theorem of the existence and uniqueness of solution to the Cauchy problem, we obtain the simple local solvability problem 6. Let us show that the solution to problem 6 is a quasi-stationary symmetry of equation 3. Let U be solution to problem 6. Consider the properties of operators. For this, we introduce the following definition. The operator M is called dissipative if given condition, and note that dissipative of the operator M is equivalent to the monacy of operator minus M. The S monacy monotony of operator minus M implies the strict monony of the operators and this dissipative of these operators. Also, then go on, consider two stationary equation 7 and suppose that exists a solution to equation 7. Let me operator M be dissipative, introduce the norm in the form on slide in co-image operator L. In view of current principle, this norm is equivalent to the norm introduced from the our space raised h. Then it follows from equation 3 that the following inequality presented on slide, where V solution to equation 3 and in view of the unequalness of solution to Cauchy problem 6, we obtain that the solution can be continuous on an interval from 0 to plus infinity. Then the following theorem is correct. Suppose that the set U0 set raised M is a simple Banach CK manifold and the point U0. Exists a solution to equation 7 and operator M is dissipative. Then there exists the unique quasi-stationary symmetry U, this class presented on slide, of equation 3 that pass through the point U0. To introduce the theorem of the existence of semigroup, consider the following definition. A set M is called a phase space of equation 3 if 1, any solution U to equation 3 belong to the set raised M, and 2, for any U0 belong M, exists to a unique solution to problem Cauchy with Sobolev type equation 3. If the set raised M is a simple Banach CK manifold, when raised M considers with the phase space of equation 3. Next, let V be a Hilbert space. Consider a family operators V, T in the form with a common domain D at V, and denote by C at V as a set of continuous operators. A mapping V with point is called a semigroup of operators is the following condition is met. We identify the semigroup V with point with this graph presented with T. And a semigroup is called contractive if this condition is met for any U and V belong Hilbert space holographic V. Introduced the concept of infinitesimal generator. So consider this definition. An operator A is called infinitesimal generation of semigroup if the condition 8 holds, where domain consists for all U belong calligraphic V such that 8 is satisfied. Having considered the result of the abstract, we can move on the general mathematical model on filtration. Let omega be a boundary domain with a smooth boundary of class. Let construct a semigroup of resolving operator of equation 3. Define a shift operator ut equal u, where u is solution to problem 6. Then ut form a nonlinear semigroup of shift operator with common domain d at u equal raised m. The generation of semigroup of operator ut is operator presented on slide F. Since the operator m is dissipative and the operator L1 is positive defined, then the operator F is dissipative and constructed semigroup is contractive. In the end, this estimate, and then finally estimate presented on slide. This completes the proof following theorem, and consider this theorem. Suppose that the set range M is a simple Banach CK manifold and point U0 and exists a solution to equation 7 and operator M is dissipative. Then exists a resolving semigroup of operator ut of equation 3 defined on the manifold M. And having considered the result of the abstract, we can move on the general mathematical model on filtration. Let omega a bounded domain with smooth boundary of class C with infinity. Consider Dirichlet problem 9 for generalized filtration Boussinesq equation 10, where equation 10 is the most interesting particular case of the equation obtained by Dexter. Here, desired function u corresponds to the potential of speed of movement of the free surface of the filtration liquid. The parameters alpha and lambda characterize the medium, and the parameters lambda can take negative value. Let consider function space raised h, calligraphic h and b, all function space defined on domain omega. It is important to note that there exists the dense and continuous embedding for given P, and this embedding where P and Q obey the following equal. In raised H, define the scalar product by formula 11, where this value, the generalized solution to the homogeneous Dirichlet problem for Laplace operator minus Laplace in the domain omega. For define engine H and engine B, exists dense and continuous embedding 7, and define the operator L and M as following in form presented in the slide. Let phi k be the sequine eigenfunction of the homogeneous Dirichlet problem for Laplace operator in domain omega, and lambda k be a corresponding sequence of eigenvalues numbered is non-increasing or taking into account the multiplicity. The following lemma shows the properties of the operators. Consider L operators L is self-adjoint, fat goal and non-negatively, and operator M dissipative and P coercive. Since the equation under consideration is degenerate, then I consider that theorem we need to introduce several differentials. If lambda more or equal minus lambda 1, the current operator L can be represented in the form. Then the image operator L and co-image operator L represented in this form, and the project P equal Q and written in the following form. Construct the set racing M in this form, and the end consider theorems on the existence of solution to the mathematical models of filtration, as well as the existence of semigroup. Theorem 1 show exists solution, and theorem 2 exists semigroup for this mathematical model. Thank you for your attention.
Thank you for your talk. Are there any questions or comments? So probably could you clarify us the general result? Your assumption is that M is a C to the power K manifold. So what is this K? So what kind of a power, how it is related to the original problem? So how you find this K, this power? Which power do you need?
1 second. Sorry.
Yeah.
This K more and equal 1. We consider operator M belong space differential equation, one differential equation.
So I see the answer to my
Okay.
question. So your right-hand side is k times differentiable, and that's why the solutions should be also, in some sense, as smooth as the right-hand side of the equation. Yeah. Can you show us equation 3 once again?
We consider that equation have one solution, unique solution.
Yes, yes. So it should be as nice as the right-hand side, as far as I understand. That's why you assume if your right-hand side is k times differentiable, then you assume that your initial data is also smooth, equally smooth, and then you consider all the rest. So can you show the equation number 3 once again?
Equation 3?
Yes, so this one.
This is a Sobolev type equation in general form. These LEM operators. U is solution this equation. And this equation degenerate and kernel L not equal 0.
But L is a bounded operator or not? Not necessarily.
Boundary, initial boundary Cauchy problem or?
No. So this operator L is a bounded operator on your Banach space, or you have many spaces. So the stupid question. So just come back to the equation number 3. So my stupid question. I guess yeah. So the problem is that. Yeah. So we cannot create L to the power -1 because kernel of L is not 0. So it is not a bijection. So we cannot just apply L to the power -1 to this equation and to return it to a standard Cauchy problem, so to say. It is a degenerate problem. Okay. Now I see. Then I have a remark that so today there will be 2 talks, one of the Rainer Picard in the afternoon session, and another talk of Sasha Trostorf. So they are working on so-called evolutionary equations. And this type of equations, it is something not the same as evolution equations. It is something else. And it also allows such type of equations as you have presented us. I'm not sure about this degeneracy or not degeneracy. I suspect that degeneracy is also possible. And I'm not also sure if they consider nonlinear stuff or only linear, but they have a general framework, a new approach and general framework, how to consider different equations. And they call such equations evolutionary equations. So probably it would be, I'm not sure if their talks are exactly about this approach, but probably it would be interesting for you to follow the talks of Rainer Picard and Sasha Trostorf and look at evolutionary equations. They are somehow related to the equation 3, which you have in your slides. Are there any other questions, remarks, or whatever?
Thanks for your remark.
Well, seemingly there are no more remarks. So thanks, Kseniia, for your talk. And now we have